Lighthouse Scientific Education presents a lecture in the Introduction to Chemistry series. The topic, density in the lab, with percent error. Material in this lecture builds upon the previous lectures, density, and math for chemistry. Overview of density in the lab. We will begin our study with the determination of density from measurements, starting with determining volume by dimension, then volume by displacement. The next topic is density with multiple measurements, including averaging and using the slope of a trend line. This can be done using a computer or graphing by hand. When dealing with measurements, there is always error. We will look at what percent error means and how to calculate it. Density from measurements. There are many ways to measure the density, that's mass m over volume v, of an object. Common lab procedures include 1. Mass by weight, volume by ruler, and dimension-based formula. That's an equation of volume for common shapes. 2. Mass by weight, volume by displacement. 3. Since density is a ratio, and when plotted correctly, density is the slope of a line. Density from slope requires a review of the line y equals mx plus b, as covered in algebra. That is the student's responsibility to review. For this procedure, we need only to remember that slope m is obtained from 2 points and is defined as the difference in the y values of the points over the difference in the x values. When plotting multiple measurements on a graph with the mass or weight on the y-axis and the volume on the x-axis, the slope of the line through the data is equal to the density. We'll do this in greater detail when we get there. Our first measured density will be using volume by dimension. This is where the mass is gotten from weighing, and the volume is by using a ruler and a dimension-based formula. Regular shaped objects have mathematical relationships between volume and dimensions like length and width and height. Consider the rectangle. Its volume is found by taking the measurement of the length times the width times the height. These are the dimensions of a rectangle. Now consider the cylinder. Its volume is found by getting the area of the circle on top. That involves measuring the radius, squaring the radius, and then multiplying it by pi. To that area, multiply the measured height of the cylinder. Many familiar shapes have known formulas or equations based on measurable dimensions, and this allows us to determine their volume by measuring the dimensions. Getting density by measurement can be broken down into 6 steps. Step 1. Get the mass by weighing the object on a balance. We should note here that while density is mass over volume, the mass is almost always going to be substituted for weight. Weight is mass times gravity, which is a force. So while the term mass is the correct use, weight will be the common use. Second, identify the regular shape, be it cube or sphere or pyramid. Find the dimension-based formula for the volume. That should be relatively easy to look up. Third, identify each dimension in the equation. Fourth, measure each of the dimensions included in that formula. The 5th step, calculate the volume using measured dimensions and the formula. And finally, calculate the density by dividing mass by volume. Let's put these steps to work. Problem 1. Determine the density of a metal cylinder if it has a mass of 7.15 grams, a radius of 0.31 centimeters, and a height of 3.0 centimeters. Step 1. Get the mass by weighing the object on a balance. We will use our basic problem-solving technique for this problem. That means mass goes into the setup as a known quantity. Mass equals 7.15 grams. Remember, this is actually weight. Next, identify the regular shape. That's the cylinder. As we saw earlier, the formula of a cylinder is volume equals pi r squared times height. And we put this formula in the equation or relationship part of the problem-solving process. Our third step has us identifying each of the dimensions in the equation, beginning with radius and then height. The fourth step is to get the measurement of each of the dimensions. If we were actually determining the density of a real cylinder, we would do that. We could treat the values in this problem as if they were measurements that we made in the lab. We measured the radius. It was 0.31 centimeters, and that goes into the setup. Our measurement of the height is 3.00 centimeters. That also goes into the setup. Now it's time to calculate the volume using the measured dimensions and the formula. We solve by inputting the values from the setup into the formula or equation. 3.1412 times 0.31 centimeters squared times 3.00 centimeters, which gives us a volume of 0.921 centimeter cubed. Note that the squaring of the radius gives squared centimeters, and multiplying squared centimeters by centimeters in height gives cubed, or 3 times centimeters, which is the same as a milliliter. 1 mil equals 1 centimeter cubed. Volume is now added to the setup. And the final step is to calculate the density. The formula for density is mass divided by volume. The solution to the problem is found by inputting the values from the setup into the equation. 7.15 grams divided by 0.921 centimeters cubed, which comes out to 7.76 grams per cubic centimeter. Now, it wasn't asked for in this problem, but we can take our calculated density and compare it to substances in a list of known element densities to deduce what our cylinder might be made of. The closest substance to a density of 7.76 grams per cubic centimeter is iron, with a density of 7.874 grams per cubic centimeter. At the end of the lecture, we will use these values to quantify how far off our measured value is from the accepted value of iron. That will be percent error. What if the material or object of study doesn't have a shape with a common formula? The solution is volume by displacement. Here we look at getting density, where the mass is determined by weighing, and the volume by displacement. For displacement, we go back to Archimedes. He noticed that when an object is submerged into water, it displaces or occupies an equal volume of water. It is said he discovered this while he was sitting down in his bathtub. What this means is that if we start with a known amount of water in a container that allows us to measure that amount of water, and we add the object of interest of unknown volume to the water, and note the increase in volume of water due to the addition of the object, we can reason that the increase in water volume is the same as the object's volume. Displacement. The increase in water volume is equal to the object's volume. Getting density by displacement can also be broken down into 6 steps. The first step is getting the mass by weighing the object on a balance. Next, add water to a graduated cylinder or such a vessel that allows the volume of the water to be measured, and note the original level of water. Oh, be sure to add enough water to submerge the object completely. After that, add the object. Note the final water level. Once those values are obtained, get the volume of the object by taking the final level and subtracting the original level. And finally, calculate density by dividing the mass by the displaced volume. Overall, quite similar to density by dimension. Problem 2, density by displacement. An unknown substance with a mass of 54.8 grams is put into a graduated cylinder to discover its volume. What is its density? Step 1, get the mass by weighing the object on a balance. Using our basic problem-solving process, the mass of 54.8 grams is added into the setup. Remember, this is actually weight. The next step is to get a graduated cylinder, add some water, and note the level of the water. This is the original level. Here we see that it is 30 mils. Add that value to the setup. The easiest step is to add the object to the graduated cylinder. Carefully Once that is done, note the final water level. It seems to be 50 mils. Add that to the setup. Now we need to get the volume of the object by taking the final level and subtracting the original level. We write the equation. In the equation panel, we solve by inputting the values from the setup into the equation. 50 mils minus 30 mils. Doing the math, that comes out to 20 mils. If you get a negative number, you have switched the order of levels in the equation. Volume is now added to the setup. And the final step is to calculate the density. The formula for density is added to the equation panel, and the density of the unknown is solved by dividing the weight of 54.8 grams by 20 mils. Density is 2.74 grams per mil. Taking our calculated density to a list of densities shows us that our unknown has a density similar to that of aluminum at 2.702 grams per cubic centimeter. Our next topic is finding a density using multiple measurements. We'll start by averaging. And this is because finding the density of an object from a single set of measurements can often be inaccurate. Taking multiple measurements increases the accuracy. Remember, accuracy is how close the measurements are to the true value. This point can be demonstrated with an example of a student's attempt to find the density of a material using 3 trials, that is, taking 3 separate sets of measurements. These sets are called the data as in information. In the first trial, the student measures the mass and volume of an unknown material. The weight is 2.61 grams. Note that the units are written in the header above the number and therefore do not need to be included. The volume is 2.56 mils, and we're not going to concern ourselves with how the volume is obtained. What we are interested in is how multiple measurements increases the accuracy of our density determination. Using the equation for density, mass over volume, gives the density of the first trial as 1.02 grams per mil. The second trial uses a larger sample of the same material, and it is found to have a mass of 5.01 grams and a volume of 4.99 mils. Its density is calculated to be 1.00 grams per mil. The last trial has a still larger sample with a mass determined at 5.82 grams and a volume of 5.89 mils. The density comes out to 0.988 grams per mil. While these calculated densities do not vary by much, they are not exactly alike. At least 2, and probably all 3 of them, are not true values. How can these results be used to increase the likelihood of a more accurate value? Averaging. Averaging of multiple measurements can increase the overall accuracy. Well, how do we average? Basically, add the results and divide by the number of trials. Okay, add the densities for the 3 trials. 1.02 plus 1.00 plus 0.988, that comes out to 3.008. Divide the sum by 3, the number of trials, and the average value comes to 1.00 grams per mil to 3 significant figures. Notice that averaging gives a value that is between the highest and lowest of the results. Density multiple measurements part 2. Another way using multiple measurements to increase accuracy is to 1. Plot the multiple measurements as points. We'll use the same set of data in this process. Plotting is a necessary ability to do well in science. This is called a Cartesian graph, and it has 2 dimensions or axes. The horizontal or x-axis shows the value of volume data, while the vertical or y-axis holds the mass or weight data. When plotting points, the x value is always written first and represents the value of the volume. The y value is written second and represents the mass value. The order is essential in this process. The second point, a volume of 4.99 mils and a mass of 5.01 grams, and the third point, a volume of 5.89 mils and a mass of 5.82 grams. Once these points are plotted, draw a best fit line. It is also referred to as a trend line because it follows the trend of the data. More on this later. And then get the density from the slope of the best fit line. The equation y equals mx plus b, with m being slope of the line and b being the y value of that point when the best fit line strikes the y-axis. It's called the y-intercept. When the value of the slope is determined from the best fit line, the m value will be the average density, d. But why is that? Density is a ratio of mass to volume. It can also be described as the change in mass, delta m, over a change in volume, delta v. Delta, the triangle, is a Greek letter and is used here to mean change or difference, as in subtraction. The density can therefore be thought of how the mass of a material changes as the volume changes. Let's return to the best fit line. The general equation of the line is y equals mx plus b. The slope is determined using 2 points from the line, any 2 points. For demonstration purposes, we will use generic points, x1, y1, and point x2, y2. The subscripts 1 and 2 are there simply to distinguish the 2 points apart. They are not numbers in the point. So, using these 2 points, begin by taking the y value of the second point and subtracting the y value of the first point, delta y, or the change in y values. Divide that by the difference of the x values. Take the x value of the second point, x2, and subtract the x value of the first point, x1. Delta x, or the change in x values. So if mass is plotted as the y values and volume is plotted as the x values, then delta m over delta v is the slope of the best fit line through the data, and it is d, density. That is the math of the process. There are 2 common ways to get the trend line, and looking at those should help clarify this slope business. And we begin with letting the computer generate the trend line. Since it is a computer, begin by entering the data, the points, into a spreadsheet, one like Excel. There are many kinds of spreadsheets, and each has its own method for entering data and plotting and so forth. The student is therefore responsible for finding out how their particular spreadsheet accomplishes these steps. The second step is to plot a scatter plot. That is, plot just the points, x volume versus y mass or weight. Now, ask the computer to add a trend line with equation. Again, learn how to do this with your spreadsheet. The equation of the line it generates will be in the form of the line y equals mx plus b. Every line has its own m, or slope, based on the angle of the line. With this line, the computer gives us a slope of 0.9689. The final step is to recognize that when volume is plotted against mass, the density is the slope of the trend line or best fit line. The density from the analysis by trend line of these 3 trials is calculated to be 0.9689. And don't forget the units. Mgs per mil. The last of the multiple measurement process is getting density from the slope, but this time using points from the fit line that is drawn by hand on graph paper. It is generally similar to that what we saw with the computer, but a little less exact. Start by plotting a scatter plot, x volume versus y mass, on the graph paper. This assumes a knowledge of basic graphing. Next, add a trend line by hand. But what makes a good trend line or a good best fit line? The short answer is that it is the line that goes through or just misses the points by the smallest amount. It is not connect the dots. We will try a couple out and see which one looks best. This looks good, but it misses the lower point by quite a bit. And this one misses the top by too much. this one, splits the difference. It misses both the top and bottom points by a smaller total margin than either of the other two lines. That's what makes a best fit line. It is the line where the sum of the difference between the data points and the line is a minimum. The process of hand drawing a best fit line is subjective, which means that there is a personal judgment in the decision. Now that we have a line, we need its slope. For this, we need to pick 2 points on the line and put their values in the equation for slope. But which 2 points? Any 2 points. Usually not the data points that fall on the line, but those could work too. We'll remove the data so that we can concentrate on the line. One way to pick a point is to start at a grid mark on the x-axis and move up to the line. Once at that line, go directly to the y-axis and then read the values. It is not necessary to draw a dotted line to get from the fit point to the y-axis, but it does tend to increase the accuracy. The first point is 3, 3.05. The 3.05 is an estimate, and it is really a bit over the accuracy we can get from this grid. But the less detailed grid is better for demonstration. On your grid paper, you will probably also need to estimate or extrapolate values that are between grid lines. Just do your best. We will refer to the 3.0 in this point as x1 and the 3.05 as y1. For the second point, let's say we start on the x-axis at 7. From there, it goes over to the y-axis at about 6.92. The second point is 7, 6.92. These are the values we will refer to as x2 and y2 respectively. Now it's time to get the density from the slope of the trend line. Remember, the slope from 2 points is the difference in the y values over the difference in the x values. Let's begin with the y values. y2 is 6.92 and y1 is 3.05. The difference is 3.87. Next, we do the same thing with the x values. x2 is 7.00 and x1 is 3.00. The difference is 4.00. Dividing the change in the y by the change in the x gives us 0.968. As plotted, the slope of the best fit line, this trend line, is the density. And of course, do not forget the units, mgs per mil. The last topic is percent error. All measurements are at least a little bit inaccurate. Percent error shows how far off an experimental or measured value is from an accepted or predicted value. Percent error is a modification of the percent equation covered in Math for Chemistry Part 2. That was part divided by whole times 100 equals percent. In the percent error form of this equation, the whole is the accepted or predicted value. The part is the difference between the accepted value and the measured value in the lab. It is how far off the measured value is. When the numerator is divided by the accepted value, the how far off is converted into what fraction off. Multiplying that fraction by 100 gives the percent error, or what percent off. One more thing about this equation. Notice that there are bars around the subtraction in the numerator. Those are called absolute values, and they make whatever is inside of them positive. Not all chemistry courses use percent error with the absolute value bars. If yours doesn't, then just ignore them. Consider the density calculated from the earlier problem using measured dimensions of the cylinder. We came up with 7.76 grams per cubic centimeter. In the percent error equation, this would be considered the measured value. In that problem, we compared that measured value with a lookup table of accepted values, and we saw that the measured value was close to that of iron. The 7.87 grams per cubic centimeter is considered the accepted value, and now we have enough information to calculate the percent error. That is assuming the cylinder is really made of iron. Insert the measured and accepted value in the numerator of the equation. Divide by the accepted value and then multiply by 100. The math in the numerator comes to negative 0.11. The absolute value sign around the negative 0.11 forces us to take the positive of that value, positive 0.11. Dividing 0.11 by 7.87 gives 0.0140, and multiplying that value by 100 gives the percent error of 1.40%. That's pretty good. Let's see how we did with the density using volume by displacement. The displacement problem gave us a density of 2.74 grams per mil. It compared favorably with the density of aluminum at 2.70 grams per cubic centimeter. Notice that the volume unit is given in mils in one value and cubic centimeters in the other. Since 1 mil is the same thing as 1 cubic centimeter, we can make a direct substitution. Referring to the percent error equation, the 2.74 grams per cubic centimeter is the measured value, and the 2.7 grams per cubic centimeter is the accepted value. Inserting these values into the numerator, dividing by the accepted value of 2.7, and multiplying by 100 gives the percent error. The math in the numerator comes to positive 0.04. No need to worry about those absolute value signs. Doing the division on the fraction gives 0.0148, and multiplying this by 100 gives a percent error of 1.48. Again, a very small percent error. Keep in mind what percent error offers. It is an indication of the accuracy of the measurements. Recapping the lecture. Density of an object by measurement. This can be done for objects of common shapes using known formulas of volume. Using measured dimension to find volume, density then follows from mass over volume. Density of an object by displacement. This involves finding the volume of an object by the water it displaces. Density then follows from mass over volume. Taking multiple measurements increases the accuracy. Averaging involves adding the results of the individual trials and then dividing by the number of trials. When multiple measurements are plotted as volume versus mass, the slope of a best fit line through the data of the general formula y equals mx plus b has the density d for the slope m. And finally, percent error shows us how far off an experimental or measured value is from the accepted or predicted values. And that concludes our lecture. Remember to practice what you've seen to truly build understanding. And with these more complicated subjects, it helps to establish and follow a process.